As you can see right now, the process begins with aluminum alloy and steel component production. Mazda officially restarted rotary engine vehicle production in June 2023, after an 11-year gap since the discontinuation of the RX-8. This rotary engine is built at Mazda's Ujina Plant No. 1 in Hiroshima City. This factory handles global rotary EV assembly. After cooling and solidifying, the casted parts are removed from the molds and undergo further machining, polishing, and quality inspection before assembly. After casting, the rotary engine parts, housing, rotor, and side plates, move into machining, where the real precision is built in and perfect sealing is set. First, the raw cast housings are clamped into CNC machines, which strip away excess material and bring every surface down to exact tolerances. This step is critical, because in a rotary engine, even the smallest deviation can compromise apex seal contact and overall compression. Rotary engine housing production involves a series of highly precision-engineered components. Apex seal grooves must be machined with extreme accuracy to ensure proper sealing and compression. All of this is built on precision aluminum castings that define the engine's lightweight yet durable architecture. Mazda uses high-precision casting and CNC machining because rotary engines demand extremely tight tolerances compared with piston engines. Even tiny dimensional errors can reduce compression or apex seal durability. Now the engine machining at this Hiroshima plant is completed, and after testing, we will move on to the next part of the production process. One of the most important production stages is the internal rotor housing coating. This is a high-speed flame spraying process used to apply durable ceramic coatings onto key rotary engine components. When these ceramic particles strike the housing surface, they flatten instantly and bond layer by layer, forming a dense, extremely wear-resistant coating. Right now you're watching the final assembly line of the Mazda MX-30 rotary EV engine come together. The engine assembly process is more handcrafted and inspection-intensive than many standard four-cylinder engines. Side housings are then added to enclose the working chambers. Apex seals and corner seals are installed to maintain compression and ensure smooth combustion sealing. Supporting systems include oil metering components for precise lubrication, along with intake and exhaust systems that manage airflow. Right now, you're watching a small team of Japanese factory workers assembling these exceptional engines. There are only a handful of them, and they're highly specialized for this precise, delicate work. In the MX-30 rotary setup, a generator coupling connects the engine to the electrical system, allowing it to function as a range-extending power source. Even small deviations can affect compression and efficiency, so the human role is focused more on precision oversight and validation rather than manual building from scratch. Rather than a large workforce, Mazda's Hiroshima rotary program relies on a small team of specialists and advanced automation to achieve the precision, its rotary EV range extender demands. Unlike traditional hybrids, the wheels in this Mazda are always driven by an electric motor. The rotary engine only generates electricity to recharge the battery or support the electrical system. The battery pack assembly process begins with the precise installation of individual cells, followed by the integration of an advanced thermal management system to control heat under load. Dedicated cooling systems are then incorporated to maintain optimal operating temperatures. Each pack undergoes strict electrical safety validation to ensure reliability and protection. Finally, the entire assembly is sealed, locking in performance, durability, and long-term stability. The MX-30 body structure is engineered around EV battery integration, advanced side impact protection, and a balance of lightweight design with high rigidity. Mazda chose a relatively modest 17.8 kilowatt-hour battery because the rotary generator extends total range. The MX-30 rotary EV powertrain blends electric efficiency with rotary innovation. While Mazda relies heavily on robotic welding for consistency and precision, human inspection stages are still built into the process to ensure every detail meets strict quality standards. A 125 kilowatt front electric motor provides the driving force. Energy is supplied by a 17.8 kilowatt-hour lithium-ion battery. And now, as a reward, you can watch the process of joining the powertrain with the upper part of the body. An 830 cubic centimeter single-rotor 8C rotary engine never drives the wheels directly. This process is commonly called marriage, but inside the factory it's officially known as the body drop. In the case of the Mazda MX-30 rotary, this step is especially interesting because it involves a compact rotary range extender system rather than a conventional large engine. Instead of complex manual wiring, most connections are designed as quick-connect high-voltage couplings. When the body is lowered, key connectors automatically align and lock into place. Mazda engineered the rotary engine specifically as a compact onboard generator. Its small physical size, naturally low vibration, and ability to run smoothly at constant RPM make it an ideal solution for steady, efficient power generation. By operating purely as a generator, the rotary engine can run within a much narrower, optimized speed band, unlike in sports car applications, allowing it to stay in its most efficient range and deliver smoother, more consistent performance. Historically, rotary engines have been associated with higher hydrocarbon emissions and increased oil consumption. To address this, Mazda redesigned the combustion chambers, refined the fuel injection systems, upgraded catalytic treatment systems, and improved apex seal lubrication. These changes were aimed at making the rotary engine cleaner, more efficient, and better suited for modern emission standards. This is how e-SKYACTIV X engines are manufactured at Mazda's Ujina engine plant. Human operators then step in for the critical finishing work: sensor installation, calibration, and final torque verification. Engine blocks move into a highly automated assembly line where robots install most components. But right now, you're watching the main final assembly line in action. Mazda runs a mixed model production system, so e-SKYACTIV X engines are built alongside other e-SKYACTIV engine variants on the same line, allowing flexible, high-efficiency manufacturing without dedicated lines for each engine type. The shaped parts are now brought together through welding, where the car's structure locks in and its form truly takes shape. Welding is performed with high precision, as it plays a critical role in the car's overall stability and strength. Robots handle much of this process, not just for efficiency, but because they deliver consistent, highly accurate results. Once the body is complete, the doors, hood, trunk lid, and other exterior components are carefully fitted into place. With laser welding, each point can be welded in as little as half a second. The higher welding speed allows Mazda to weld more points, strengthening the body and improving the car's dynamics and stability. At the Hiroshima Ujina plant, Mazda intentionally avoids full automation. The approach is to use machines for consistency and people for sensitivity. This MX-30 is not Hiroshima's primary model, so only about 70,000 of these vehicles are produced here annually. Inside this Mazda Ujina plant in Hiroshima, the Mazda CX-5 is primarily assembled on the production line. Right now, the process you're watching shows a large panoramic sunroof being carefully installed from the interior side of the vehicle. At this stage, the roof system arrives as a fully sealed and pre-assembled unit supplied by specialized external manufacturers, ready for precise fitting on the assembly line. Mazda has made the CX-5 one of its key global models, with the vehicle accounting for roughly 25% of the company's annual sales. The plant itself operates at a high output level, producing over 240,000 units of this model each year. On average, that works out to more than 600 vehicles being completed every single day at this facility. Typical CX-5 production at the Ujina plant includes stamping, robotic body assembly, painting, e-SKYACTIV powertrain production, final assembly, and quality inspection. This is how a typical Mazda CX-5 front grille is easily mounted by simply snapping it into place. And now comes the final stage of the manufacturing process. This is the quality inspection inside the LED tunnel. Quality inspectors are specially trained professionals who are certified to perform inspections within a set time limit. These inspectors are trained to detect and visually confirm panel gaps as small as 0.1 millimeters. This level of precision demands intense focus and a highly trained eye. The Quality Control Department serves as the final line of defense, ensuring that every vehicle meets strict standards before it is approved for delivery. Production of the CX-9 began in 2006 at Mazda's Hiroshima facility for the North American market. The model is exclusively manufactured in Japan at the Ujina plant, number 1 in Hiroshima. This makes the CX-9 a Japan-built export model, with no regional manufacturing variations in quality or assembly standards. It has never been mass-produced in the United States or in any other country, reinforcing its status as a globally exported vehicle built entirely at its Japanese production base. This Mazda typically uses a 2.5-liter SKYACTIV G turbo engine. It is built at the same Hiroshima engine plant and synchronized with the vehicle assembly process. The Hiroshima plant employs around 10,000 workers across its operations. The workforce includes assembly line operators, engine plant staff, and specialists in welding and paint shops. Both all-wheel drive and front-wheel drive Mazda CX-9 models share the same production line, built side by side through the same process. It also relies on logistics teams, quality control inspectors, and engineering support staff. Together, these groups keep every stage of production running smoothly, from initial assembly to final inspection. It stands as Mazda's largest single industrial site in Japan. Mazda's e-SKYACTIV all-wheel drive system combines advanced sensors with predictive torque control to respond to changing driving conditions. Its calibration is built into the production process itself, not just treated as a final hardware installation step. This integration ensures the system is precisely tuned as each vehicle is assembled. Mazda follows the Japanese concept of monotsukuri, which means crafting things with skill and spirit. In practice, engineers and assembly line workers work closely throughout the production process. Workers on the line are also encouraged to suggest improvements and refine how things are done. As a result, quality is not treated as something checked at the end, but as a craft that is built into every stage of production. This stage is called finished vehicle storage and port logistics, and it is a key part of Mazda's export system. Cars are driven to large outdoor parking areas inside the Hiroshima complex. At Hiroshima, these yards are located near Ujina Plant No. 1 and No. 2. They are also directly connected to the port logistics zones. Ships do not arrive every hour. Vehicles are stored until a full vessel load is ready. They are also organized into destination batches, such as for the USA or Europe. Unlike some manufacturers, there is no need for long inland transport to a separate port. Cars remain within Mazda-controlled areas until they are loaded onto ships. Welcome inside the rotary engine assembly line at Japan's Hiroshima engine plant in the 1990s. Right now, you are watching the production of a 1.3-liter twin-rotor Wankel rotary engine. This engine was introduced in 1991. It was the world's first mass-produced sequential twin-turbo engine. Over 100,000 of these engines were produced. This number is very similar to the total number of Mazda RX-7 cars that were manufactured. As this particular engine is the Mazda 13B REW rotary engine, which was produced from 1991 to 2002. It debuted in the third-generation Mazda RX-7 and remained in production until the end of RX-7 production in Japan. One interesting fact is that Mazda hand-selected and measured many critical rotary engine components much more carefully than was typical for piston engines. Rotary engine assembly required very tight tolerances for rotor housings, apex seals, and eccentric shafts, and experienced technicians performed much of the precision assembly and inspection. This attention to detail is one reason the 13 BREW became one of the most respected production rotary engines ever built. This engine wasn't built like a typical piston engine with loose tolerances. Mazda treated it like a precision instrument. Every rotating part, such as rotor housings, eccentric shaft, apex seals, and clearances, had to be perfectly matched. Even tiny deviations could hurt compression and sealing. Rotary engines depend on apex seals, so rotor housings needed extremely precise finishing. Even tiny flaws could hurt compression or cause wear, so quality control was much stricter than in typical piston engines. Mazda stopped installing the 13 BREW in new production cars after 2002. However, it has continued to supply replacement engines and parts for enthusiasts through its motorsports and parts programs. As you can see right now, the manufacturing procedures and hand assembly processes used for these rotary engines in the 1990s were very similar to how they are carried out today. There are, of course, differences in tools, measurement technology, and production efficiency, but the traditional method of careful, precision-based assembly has remained largely unchanged over time. In the 1990s, Mazda sold more vehicles overall, especially during Japan's stronger domestic automotive market period. At that time, Japan's economy was larger in terms of domestic car demand, and Mazda also had a broader lineup and higher production volumes globally. This is the Ujina plant, which is one of Mitsubishi's key powertrain production facilities in Japan. It is part of Mitsubishi's broader engine and transmission manufacturing network. At Mitsubishi's Japanese engine plant, production follows a highly standardized and automation-heavy process, while Mazda integrates engine manufacturing more deeply into its vehicle development philosophy and in-house tuning culture. The plant is focused on automotive engines, engine machining and assembly, and in some configurations, transmissions and other powertrain components. It is not a vehicle assembly plant, but rather a dedicated powertrain facility focused strictly on engines and related components. This factory employs roughly around 1,200 to 2,000 workers in total, depending on the source and how on-site contractors are counted. The Kyoto plant is known for its integrated production flow, where engine components are cast, parts are precisely machined, and final engines are assembled in a continuous system designed for high accuracy and consistency. It is one of Mitsubishi's dedicated engine facilities in Japan, supporting multiple Mitsubishi global models with powertrains. The plant combines highly automated machining with skilled manual inspection and is built on aerospace-derived manufacturing know-how that emphasizes a precision-focused production culture. These engines are used in models such as the Mitsubishi ASX, Eclipse Cross, earlier generations of the Mitsubishi Lancer, and the Outlander, serving both standard petrol and mild hybrid applications depending on the market. This Mitsubishi factory produces mainly inline-4 gasoline engines used in compact and mid-size passenger vehicles. It focuses heavily on Mitsubishi's variable valve timing system equipped designs, where variable valve timing improves both fuel efficiency and power delivery. This plant produces mainly 1.0 to 2.4-liter inline-4 gasoline engines, including small efficient 1.0-liter turbo units for compact city cars and larger 2.0-liter to 2.4-liter naturally aspirated. The facility specializes in precision machining and high-tolerance assembly, ensuring consistent engine quality across global models. Some of its engines are also designed for integration into hybrid systems, supporting Mitsubishi's electrification strategy. It does not build heavy-duty diesel or performance-focused engines, but instead concentrates on high-volume powertrains for everyday cars. It is considered a high-volume mass production site, operating continuous mixed-model engine production, where different engine types are built on the same lines. Like most major Japanese engine plants, output is typically estimated in the hundreds of thousands of engines per year, rather than just tens of thousands. On a daily basis, this generally translates to several hundred to over 1,000 engines per day, depending on demand and model mix. Each engine then undergoes cold and hot testing, including leak checks, rotation resistance measurements, and performance validation before being shipped to vehicle plants. Final assembly is highly automated, with robots handling bolt tightening, sealing, and movement between stations. Large steel body panels were first stamped under massive hydraulic presses before robotic welding systems assembled the chassis with high structural precision. The Mitsubishi Lancer Evolution Final Edition marked the end of one of Japan's most iconic performance sedans. Production took place at Mitsubishi's Hiroshima plant in Okayama, Japan, the same facility responsible for building the Evolution X platform during its final years. Only around 3,100 final edition cars were produced worldwide, making it one of the rarest modern evolutions. But now, you're watching the body panels of the latest Mitsubishi Lancer Evolution Final Edition being stamped into shape. What made the final edition special was not just its rarity, but the fact that it represented the most refined version of the Evolution X formula. Japan received 1,000 units, the United States received 1,600 numbered cars, and Canada received 350 examples. Each vehicle carried an individual production plaque inside the cabin, emphasizing its collector status. Mitsubishi also equipped the car with Bilstein dampers, Eibach springs, Brembo brakes, lightweight wheels, and the company's advanced Super All-Wheel control system. The cars were built on mixed model production lines, but final edition units received unique trim components, serialized badging, black roof panels, darker exterior accents, and specially stitched interiors during final assembly. Unlike ordinary Lancer models, these vehicles were treated as halo performance cars, with additional inspection standards applied before leaving the factory. The Evolution line itself became famous because it blended rally-derived engineering with mass production. By the time the final edition arrived, it had become a farewell tribute to Mitsubishi's golden era of performance engineering. The Mitsubishi Lancer Evolution Final Edition was manufactured inside this Hiroshima plant using a production process that combined high-volume industrial automation with additional performance-focused inspection procedures. Because the Evolution platform was designed around high-performance all-wheel drive dynamics, body rigidity and weld accuracy were especially important during production. Inspectors checked body panel gaps, paint consistency, drivetrain calibration, and interior fitment with greater scrutiny than ordinary production cars. Each engine also underwent testing for oil pressure, idle stability, turbo response, and electronic fault detection before installation. At the end of the line, every completed vehicle passed through final inspection stations under intense lighting conditions, where technicians visually examined paint surfaces, reflections, and body alignment. Because the final edition marked the end of the Evolution lineage, Mitsubishi treated the program with unusually high attention to detail. Many enthusiasts consider these cars among the most carefully finished Evolution X models ever produced. Road simulation rollers and diagnostic systems were also used to verify drivetrain behavior, steering response, braking systems, and all-wheel drive functionality before the cars were approved for shipment.